All right, so today we are going to look at inertia, right? So, remember what inertia was? What was inertia? If an object is in motion, what will it do? Stay in motion. What is the tendency of that called? Inertia. So inertia is the property of objects which resist changing the state of motion, right? If things have a small mass, it's easy to change their state of motion. If they have a large mass, it's hard to change their state of motion, right? That was inertia. So if a train is going 25 miles an hour down the track and it's got lots of mass, it is very hard to speed it up, slow it down, or change its direction because of its inertia, right? Okay, well, when systems rotate, so my analogy was, which one do you want to headbutt? You want to headbutt the tennis ball? What's the difference? Yeah, inertia. This thing's 4 times heavier, right? It has a much stronger tendency to keep moving towards your brain instead of bouncing the other direction, right? So that's inertia. Now, when you rotate things, they also have inertia. So inertia, rotational inertia, is the property of an object to resist changing its angular motion. So if I were to take this thing and I could turn it, okay, right? But I gotta exert a pretty good torque to make it twist, right? And then I gotta exert a torque to stop it again, right? So this has rotational inertia. If it was spinning, it would tend to keep spinning, and you'd have to apply a torque to make it stop spinning, right? What do you think its inertia depends on? It's rotational inertia. What do you think that depends on? Well, what does regular inertia depend on? Mass. So rotational inertia depends on mass. If this was a heavier bar, it would be harder to start it spinning, and it would be harder to stop it, right? Is there anything else that matters? Yes. The radius always matters in anything angular. How does the radius affect it? Because if I take these 2 weights and I put them in the middle, the total mass of my bar is still the same, right? You agree? But what happened to the rotational inertia? What happened to the tendency to keep spinning? It's a lot easier. Okay? So I'm going to pass this around. Just make sure they're nice and snug before you start messing with it. Put them in the middle and flip it back and forth. See how much torque it takes to change its rotational motion. And then move these 2 to the outside. Snug them up again so they don't go flying off and decapitate you. You guys hear about that ceiling fan model they had to recall? The blades kept detaching. Apparently this is a thing. Like, half the nation has a phobia about their ceiling fan coming loose and chopping their head off. And it's actually happening. You guys ever worry about that? Me neither. It never occurred to me. But anyway, put them on the end and feel the exact same mass, but it's distributed differently now. It's farther from the pivot, and it's harder to get it turning, and it's harder to stop it. Okay? So rotational inertia depends on mass, but it also depends on where it's located. Okay? So just go ahead and try that. Pass it around as we go through this. Swing them back and forth a couple times. Move them to the middle. Swing them back and forth. Okay. So let's just kind of loosen the nuts there. Lefty loosey, righty tighty. So we're going to do a thought experiment for a lab today. But before we do, let's get set up a little bit here. So give me 10 seconds to get my presentation up. Okay. You do both of them? Big difference.
Yeah.
Big difference. All right. So, did you put them all the way together?
Not all the way.
Oh, put them all the way to your hand. It's crazy how much difference there is. Yep. All right. So, rotational inertia. Rotational inertia depends on the mass and where it's located. Okay? So, the location of the mass is always measured relative to the axis of rotation, like where you're rotating about. So in this case, we're pivoting that stick about its middle, right? When we go like this back and forth. Now, if you have a single point, an object that is in a small space, okay, then I've got some small mass here. It is located at a distance r from the pivot. So this would be like a light stick with a heavy chunk of matter on the end. The moment of inertia turns out to be given by m times r squared. So not only does the distance matter, it matters twice. It's double. I mean, it's squared. Okay? So if you have a point mass rotating around an axis of rotation, the moment of inertia, how much inertia it has, is not given by mass, it's given by mr squared. Okay? You good with that? All right. Now, what would happen if you had a couple of different masses rotating around a point? How would you find the moment of inertia? What's your guess? Yeah, you're just going to add them up. You'd find the moment of inertia of this guy, so take this mass times this distance squared, plus that mass times that distance squared, plus that mass times that distance squared, and you'd add them up. So it would look like this. Okay, you guys starting to feel comfortable with that notation? Take each mass times its distance squared, and add them all up for all the masses. Okay? What would happen, though, if you have a solid object, like a board? How do you find the moment of inertia of a board? Well, a board, like, where's the mass? It's spread out over the whole thing, right? Can you treat it like it's all in the middle? I don't know. So what we're going to do is we're going to take our board and we're going to divide it up into a bunch of little chunks. And this little chunk here, its mass is at the middle, and its distance is here. And then you can think about that chunk, and that chunk, and that chunk. You could break it up into a bunch of little chunks, and you could find the moment of inertia to each of the chunks and add it up. And you get an approximate moment of inertia for a solid object. See, this formula only works for point objects. If all the mass is located at a point, and you can measure how far that point is from the axis of rotation. But if we have an object where the mass is spread out, we're going to do a little more work. Okay? So calculus tells us we could find the moment of inertia by simply adding up the contribution of every little chunk. Okay? And so that's what we're going to do. Okay? So, where's those all that? I don't want that. Okay. So, here's what we're going to do. We are going to do a thought lab where we are going to take a board and we're going to break it into some sections and try to find the moment of inertia of each section. Okay? When we're done with that, it'll take us about 45 minutes. We'll come back and tie this all together. Okay? So go ahead and grab your computer and find lab 7.2. Go ahead and log in. So you're going to have a board. We are going to try to find its moment of inertia around one end. So I tell you the mass of your board, and I tell you the length of your board. Is that right? Yeah. Okay, now, we're going to pretend like all the mass is right in the middle. If all the mass of that board was right in the middle, what would be its moment of inertia? Well, to find the moment of inertia, you just take each mass times the distance from the pivot squared. So what would be the mass of this? Whatever your mass is, right? Yeah. How far is it from the pivot? If all the mass of the board was in the middle, how far would that be from the pivot? Your board is 1 meter long. So it'd be what? 0.5 meters. So take your mass times the distance, 0.5, squared. That's the approximate, that's our approximation of the moment of inertia. Thanks. You guys all feel that?
Yeah.
It's a big difference when you move the same weights farther out, right? Okay, everybody got part 1A? Yeah? Okay. Now, let's do 2 chunks. Let's divide this into 2 chunks. So now we have 2 pieces. Pretend like the center of each, so think about this piece here. Its mass is half the mass of the meter stick, and it's located how far from the pivot? 0.25 meters. And the other section, you know its mass, it's half the mass of the meter stick, and how far is it located from the pivot? Okay, so take each mass times its distance squared and add them up, and you'll have the moment of inertia. And then keep going. And very soon, you're going to get tired of your calculator. Getting tired of your calculator?
I'm not doing a part E, Mr. Blatchley. I refuse.
Part what?
1E. I won't do it.
Don't you know any computer science?
I mean, but not with the calculator.
Getting tired of your calculator yet? Anybody ready for a new tool? Luke? Are you on 10?
No, I'm 5.
5? You're tired of 5?
Yeah.
Oh, man. Okay, guys. So we agree that a calculator is not a very good tool. You're doing something very similar over and over again, and that just screams computational aid, right? We're going to use spreadsheet. So, open a new window, type sheets.new. I'll open a new Google Sheet. You guys know that trick? You type sheets.new or docs.new, it opens a new document, or slides.new. Go ahead and open yourself a new spreadsheet. And let's think about how we would do this with a spreadsheet. Because if we could write a formula in our spreadsheet, we know that copying formulas down is super easy, right? Yeah?
Yeah.
Okay, so let's assume that our mass is 0.78 and our length is 1. And let's do 5 chunks. Okay? So I'm just going to go 1, 2, 3, 4. Here's my 5 chunks. Now, what is the mass of each chunk? How would we find it? Louder, Audrey.
Divide the mass by 5.
Yeah. We want to take the mass and divide it by 5. Right? Now, we got to be careful. We can't copy that formula down. Because we said take D2 divided by 5. See right here it says D2 divided by 5? When we copy that, we don't want to take C2 divided by 5. So we're going to put dollar signs in front of the D and the 2. You guys remember that? Putting having dollar signs in front means when you copy a formula, it doesn't change the reference. So there's the masses. So I'll call this chunk number. This is the mass. Now, how far from the pivot is that chunk located? So now we need to do a little bit of thinking here. If you have 5 chunks, here's my bar. It's got 5 chunks. How far is the center of the first chunk from the pivot? It's what? It's 1/10. If we're going to divide this into 5 chunks, this is 1/5 of the length. And that is half of that, which is 1/10 of the length, right? So we can say the distance of the first chunk equals 1/10 times the length. Okay? Now, how far is the next chunk over? The middle of the next chunk. This is 1/10 of the length of the ride. How far is it from here to here? How far is that going to be? This is 1/5. Is it going to be 2/5? No, it's going to be 3/10, or whatever it used to be plus another 1/5, right? That's the route I'm going to go. So the center of the second chunk is going to be the distance to the center of the first chunk plus the length over 5. And when I copy this down, I don't want to change that length. D3 is going to be an absolute reference. So if I copy this formula down, there I have the distance to the middle of each chunk. Does that make sense? Now, let's find the moment of inertia of each chunk, the MOI, the moment of inertia. So we take the mass times the radius squared, so to the power of 2. That's the moment of inertia. And then, to find the total, we just take the sum of all of these. And that would be the total moment of inertia for 5 chunks. And now that we've got it with 5 chunks, I think you could probably figure out how to do it with 10 and 100 without driving Alex completely insane on his calculator. Okay? Give it a try. I'll leave you there for a little while.
I did not get that.